Good morning, everybody, and welcome to this session. Today is October 17th, and we are in week 6. No, I'm sorry, we started week 7. So we are in week 7, and the concepts that we're covering this week are actually related to actually continuation of what we've been covering so far in terms of applications of Newton's laws of motion. And just to give you a reminder, excuse me. So far, we have explored the 3 laws of Newton. And when we first did them, to be honest and to be specific about them, we explored them in the one-dimensional case, meaning that I have an object that is constrained to move on a single line. So that is where we talked about the fact that if an object is under no net forces, the object will maintain its motion in that same direction. When an object is actually under net forces, that is when the second law came in a sense that that object will accelerate, and its acceleration is given by the ratio of the net force over its inertia or its ability to resist that change in motion. Then, excuse me, the third law comes in when 2 objects interact. They do so in such a way that if one exerts a force on the other one exerts a force that is equal in magnitude but opposite in direction. The entire story actually was told on a single line. Then we saw actually it's not restricted to that case. I mean, that's the chapter after that, where we saw that actually this stuff still applies to the case where we have an object moving in not necessarily one dimension, in a multi-dimensional, basically, configuration. For that, we took the simplest case, which is a 2D, without loss really of generality, because more dimensions will introduce more complications, that's all. So we explore 2 cases. The first case is the circular motion. So what happened in the circular motion? You have 2 types of acceleration. Acceleration along the path, which is going on a circle around some sort of a center, and that is what we call the tangential acceleration. The reason why it's a tangential acceleration because it's really tangent to the path. As a path curves, the acceleration is along the tangent of that path, not exactly on the path, because the path does not stay in the same direction. It changes over time. So as it changes, the direction, the acceleration changes with it and stays always tangent to the path as it changes. So that is one component of the acceleration. There is a second component to the acceleration, and that is actually the most important one, and that is the centripetal acceleration. In the case of the centripetal acceleration, it is what is causing it to curve to begin with. So there are 2 types of acceleration. One may or may not be there, namely the tangential acceleration could be 0 in a sense that the object does not really change its speed. It's not gaining speed, it's not losing speed. So in this case, its tangential acceleration is 0. But the centripetal acceleration, as long as we have a motion along the curve, which is part of a circle, as long as we have a circular motion or part thereof of a circular motion, we do have centripetal acceleration no matter what. So the tangential acceleration can be 0, in which case it's a special case of a circular motion that is a so-called uniform circular motion. In a sense, we're going on a circle without gaining speed. It's maintaining its speed. But the velocity changes because of the fact that the velocity is a vector, and at any given point, it's pointing in a different direction than the previous point and the next point. So the second one, the centripetal acceleration, is the one that takes care of the direction that is changing over time. And the centripetal acceleration is proportional to the square of the velocity and inversely proportional to the radius of the curvature. So we gave an expression for it, and we even attempted to explain, without going into a lot of details, especially mathematical details, into what happened when a person takes a curve. And if you notice, when you're going, for example, driving, the speed limit might be, let's say, for example, 50 miles per hour. The minute you get into a curve, usually the speed limit is less. They drop it to, let's say, for example, 35 miles per hour. But even more so if the curve is actually sharp, they even drop it lower. let's say 25, sometimes even 15 miles per hour. And I have in mind a specific intersection here in near Redlands, where actually it curves so much that the speed drops to 15 miles per hour. Everywhere else, it's like 45 miles per hour. And then at that point, it drops to 15 miles per hour. Why? Because of the square of the velocity. Remember, the square is in the numerator. So the more, if you double the velocity, the acceleration quadruples. Because you take 2 times 2, it becomes 4. If you triple the velocity, the acceleration actually gets 9 times as much, because 3 times 3 is 9. So it is important to take care of that, to slow down in the curve. Otherwise, there might not be enough friction with the road, or might not be enough basically leaning of the road as you're turning to retain you, to keep the vehicle on the road. That is the square of the velocity. It's in there also where you have the radius, in the sense that a sharp turn will have a lower radius than a wide turn. A wide turn have a bigger radius. And if you divide the square of the velocity by a bigger radius, in this case, you will get a smaller number, versus if you divide it by a smaller number, then the ratio is actually higher. Think about it. If you divide a number, let's say, for example, I have 10, and I want to divide it by 10. 10 divided by 10 is actually equal to 1. Whereas if I divide it by 1, which is a very small number compared to 10. So if I divide 10 by 10, I get 1. But if I divide 10 by 1, I get 10 times as much. So in a sense, also the radius plays a major role. So it's a combination of the square of the velocity and the radius, inversely proportional to the radius of the curvature, that gives me that centripetal acceleration. And it is immediately connected to F equals to ma, because that's the ma part of the whole problem. So you need the force, and that force needs to be equal to ma. And a in this case is v squared over r. So in order not to slide the curve as you're going around, you need the force of friction that must be at least equal to the mass of the vehicle, or the mass of the truck that's going around, times the square of the velocity that the truck is moving with, divided by the radius. So if there is not enough friction to overcome this force, then the truck will slide, or the vehicle will slide to the other side. So it's still F equals to ma. So you need an F on one side to compensate for the ma on this side, and a is v squared over r. So you need that. Otherwise, m times v squared over r will win, and that is what we call the centrifugal force. So it's important to relate these topics together. This is actually still F equals to ma. There will be another force also in case that, say, for example, the person is accelerating. So you need another force along the tangent to compensate for m times at, the acceleration along the tangent. But in the uniform motion, if you maintain your cruise control, for example, not to speed up or slow down, if you're going on a curve, then all you have to worry about is mv squared over r, which is a big deal. Okay. So again, there are two ways of overcoming this problem, especially on curves. Either you put a lot of friction on the gravel, on the road itself, to make sure that the car does not slide. And that's why it's actually more dangerous after rain, because the road becomes slippery if there is less friction. So it becomes more of a hazard to speed up on the curves. See the connection in here? It's very intuitive, but there's actually a relationship with what we're learning in here to understand everyday experience. There is another technique actually that is called banking the roads, meaning making them incline a little toward the direction of the turn. If they are turning this way, you're going to incline them this way. If you're turning in the opposite direction, you're going to incline them the opposite direction, depending if you're going right or you're going left. And again, that helps because you add, in addition to the friction, you add also the components of the weight of the vehicle as it is moving along that direction, that direction to help you stay. In other words, the vehicle will be if the vehicle is not moving and there is no friction, the vehicle actually will slide through, okay, to put it on an incline. But what you want to do is actually, as the motion is going, that's basically to compensate for that slide. So that's what I was talking about, too, the effects of gravity. The other thing also that comes into play is the other topic that we covered actually there last time was actually the projectile. The projectile is a different kind of multidimensional motion because you have two motions along two axes in the same time. One axis is the vertical axis, and that is governed by F equals to ma, and the F in this case is the weight of the object, the mg. But the F equals to ma in this case, so mg equals to ma, cancel the m from both sides, and so then you have the value for the acceleration, which is just the gravitational acceleration, namely 9.8. So in this case, on the y-axis, we have F equals to ma, and it's beautifully working, and there is no problem with it. And that is uniformly accelerated motion. You drop an object from a certain height, and it's going to start accelerating toward the ground. Versus the y direction, the x direction, I'm sorry, where there is no acceleration. The object sails through with the same speed. So if you throw an object straight up, it's going to come down straight down. There is no problem with it. If you throw an object straight on the horizon, on the parallel, in this case, and if there is no gravity, that's a condition. So you have to do this experiment outside of the influence of the Earth or any object that has gravity. Even on the moon, it will not work. So you have to do this in empty space. Throw an object in one direction, is going to stay in that direction forever and ever and ever. And that is the first law. So you have two laws working for you in this case. The x-axis is actually the first law of Newton, namely no net forces, no acceleration. The object maintains speed as it goes along the x-axis. But on the y-axis going up, it's actually subject to the force of the gravity, so it's going to slow it down. With the assumption that there is no air resistance. If there is air resistance, then I have force along the x direction and the y direction, and the problem is more complicated than this. So what we saw there is there are a lot of descriptive terms that I can use for it. The time of flight, how long does it stay in the air? We saw the range also of the projectile, and we saw the maximum height. Those are typical questions that we want to know. How high would the projectile go in the y direction? How far will it travel in the x direction? And how long will it stay in the air, suspended in the air? It's going to take as much time going up and as much time coming down. So the other question that is typically asked is how long does it take to reach its maximum height, which should be half the flight time, because by symmetry, if there is no air resistance. So this is the projectile motion. Again, it's an exemplification of Newton's laws, and it's actually both laws, the first and the second law, applied at the same time. We didn't have really enough time, and probably are going to cover that down the road. To explore another example for the third law, namely in its full glory, and that is the motion of the rocket as it is lifting during the liftoff. So it's going to eject a lot of gas, push against the ground, and as it's pushing against the ground, as it's pushing against the grass, the gas, the engine compresses the gas basically and burns it, and it's going to emerge with tremendous speed from the vehicle, from the launch, from the launch vehicle. Yes, so it's basically trying to get the gas very fast out of it, and then the gas in this case is pushing it back. So you push on the gas from the vehicle, and the vehicle is pushing back. Just like if you take a balloon, for example, you blow a lot of air of it, and you let go. During that moment, the air is trying to escape from the balloon because there is a difference of pressure. The outside pressure is less than the inside pressure in the balloon. So the balloon is trying to push because of the high pressure, trying to push the gas outward. The gas is pushing the balloon, and the balloon flies every which way depending on the how it reorients itself in the space. So this is an example of the third law of Newton. We didn't do this in two examples, but hopefully we might cover some of them down the road. Okay. Enough examples at this point of this stuff. The next two topics are extremely important also that we're covering through this week. This week we're going to cover two topics. As a matter of fact, there is a third topic because of the fact that we have lab today. And lab today deals with the energy. So let me try to share. I don't have my pen with me, so I'm going to share with you the discussion using the mouse. Hopefully it's going to work fine. So let me go to the screen and share my notes and see. So there is the kinetic energy. Let me get into the drawing in here. So there is the concept of the kinetic energy. and the concept of potential energy. So this is potential. I'm sorry, as I was saying, I'm using a mouse, okay? And this is kinetic. And the concept of total energy, which is the sum of these two. So the E in this case is the sum of the two. So this is the total energy, which is the sum of potential and kinetic together. So kinetic energy plus potential energy will give me what is known as either the total energy, or in this scenario, which we're going to call the mechanical energy, because we're dealing with mechanical systems. Why do we have to introduce energy? Because this is actually an alternative option to doing F equals to MA. So you could do F equals to MA as part of the stuff that you work with on a regular basis, and you could solve problems, and you could do all kinds of descriptions of your of the problems that you're doing. By the way, for the lab today, and I know I sent a message before, you will need the data. You need the strip that you get from the free fall. It has all of the data that you need for this lab. So please bring it back with you. I know I sent you a message before it, so please bring it with you. If not, at least you need the data, because you were supposed to do the lab anyway for the free fall, and you would have collected the data for the different positions as the mass is falling, as you dropped it, and it falls for certain height. So you were given at different moments, actually, what, 1/60th of a second. So you're pulling data as it's coming down, and you were tracking its position in space. So this is where it starts from. And then this is after 1/60th of a second, you have a second recording and a third recording, and so on. So you have about 28 points as it fell down, basically, that were recorded from top to bottom. You will need this data to explore these two things, because in mechanics, the potential energy due to force of gravity, again, is equal to mass times the acceleration of the Earth times the height. So you need to know where the height is. So you need to know how far is the object from the lowest point in this case, and that is height. So if your starting point is 1.5 meters, your initial height is 1.5 meters. If it dropped by 10 centimeters, it's going to be 1.4 centimeters, 1.4 meters, and so on and so forth. The mass must be in kilogram, G is 9.8, and H must be in meters. So this is in meters, this is 9.8 meter per second, and this is kilogram. So the energy, if you do that, is going to come naturally in the proper units for the energy, which is joule. Also, you need the kinetic energy in this case. The kinetic energy is going to be 1/2 times the mass times the acceleration, times the velocity squared. I'm sorry, 1/2 mass times the square of the velocity. So if you measure the speeds in here, which you just can take this minus that divided by, we did it for after 2 points, yes, divided by the time, which is in this case 1/30th, because it took 1/60th to move this way and another 1/60th to move this way. So it took 1/30th of a second to go from the first to the third. So you take the last position minus the initial position, and you divide that by 1/60th, meaning you multiply by 30, because if you divide by an inverse of a fraction, you multiply by its reciprocal. So in this case, you're going to multiply by 30, and you're going to find the speed, provided you're using in meters per second, something meters per second. And the reason why we just skipped this point is because we want to call this point as our middle point. This is our first time. And we were calculating the speed that way. So we need to find the speed as it's moving. Initially, it has no speed. So when we'll first launch it, it has 0 speed. When it impacted the ground, this is really what matters in here. When it impacted the ground, it has some velocity, which we can measure. If you take these two quantities, okay, the velocity at any given point, or the velocity at the end minus the velocity squared at the beginning, this is the change in kinetic energy. So the point being in here, after you take this data, after you find the velocity, after you find the kinetic energy, and after you find the velocity, after you find the heights, and you compute this number, the potential energy and the kinetic energy, you will notice that they hardly change. That means E is for all the purposes is constant. So that's just an head start on the lab. I'll try to upload this video as soon as possible before you guys come in, so that you will have at least this discussion here, so that you understand. And we'll discuss this more in the lab anyway. So the total energy is more or less constant because there is no other mechanism for loss of energy or gaining more energy. So this is just a word about the other concept that is covered this week, and it has to do with the lab. So hopefully we will have this discussion in more details in the lab. Anyway, so the two concepts that are explored this week are the concept of the force of gravity and the concept of also momentum. Okay. So let me give a little bit of historic. I know that you guys have read the book and you're going through the book, and it gives you a lot of details into the thinking of Mr. Newton. The only trouble with this one is that really Mr. Newton never documented exactly how his thinking went. There were some hints that he was sitting under a tree, or at least that's what the word myth basically was reported, that he was sitting under a tree and somehow an apple fell on his head, and all of a sudden he came up with this expression saying that the force of gravity is given by this number G times the mass of the apple, which I'm going to label it M1, times the mass of the earth, which I'm going to label it M2, divided by the radius of the earth squared, or the distance from where the apple fell to the center of the earth squared. Okay, so this is the law of gravity that we're going to explore. Okay? Most likely this is not true, because but there is some truth to the apple, in the sense that Mr. Newton actually was trying to understand or trying to explain the three laws of Kepler. So we really need to understand the historical context into where this came through. So Mr. Kepler, before him, actually people believed, okay, Aristotle, and with my mouse, the mouse. Okay, it's in here. I have to scratch something. Let me get a thicker mouse in here, maybe this one. Okay, anyway, so the point being in here, before Mr. Newton was Mr. Kepler. So Mr. Kepler, first of all, had three laws: 1, 2, 3. But before we get into Mr. Kepler's laws, we really have to get into Aristotle, okay? And before him, Ptolemy and everybody else, okay? Actually, Ptolemy came after Aristotle. So the thinking was that the Earth was the center of the solar system, at least, because if you go day and night, you notice two kinds of stars. So this is the Earth. At that time, it was not even believed to be. No. The argument was that the Earth was spherical. So they made the case that the Earth is actually a big sphere, okay? And Aristotle's argument was basically, if you look at the sailing on the sea, the boats basically start to disappear from the bottom up, meaning that they start to fall below the horizon from the bottom. If the Earth is flat, he argued, the boats might get smaller and smaller and shrink in size, but they must stay both from the top and the bottom. They must stay visible. So if you could see the top, you should be able to see the bottom. It doesn't make sense that the bottom disappears or the top disappears in this case, which is kind of weird if it happens. But the point being in here, they must shrink in size. Initially, they do shrink in size, but then all of a sudden, the bottom starts to disappear. And the same thing, he says, that if you're coming on the boat and you're coming to the shore, for example, the mountains and the hills underneath, I mean, that you start seeing, or at least the shores that you start seeing, you're going to see them from the top to bottom. So you're going to see the top of the mountain, and as you get closer and closer, you're going to see until you see the entire shoreline. So his argument is, this proves that there is a horizon that is rising in and out over a curvature. So the Earth must be curved. He argued also based on the fact that as you travel further south, you will see stars that you don't see when you are up north, and vice versa. That means that as you go around, some of the stars that are right now hidden because they're below the horizon, below your own horizon, depending on your latitude, of course, they start to appear again because now they came up of your horizon. But the stuff that was actually above your horizon when you were up north now starts to fall below your horizon. Again, there was some argument based on that, and now he was convinced, and everybody else in antiquity, just before the advent of modern technology and YouTube, basically, I'm not blaming YouTube. I mean, the people who try to take advantage of basically these things so that they can post nonsense stuff online. He knew then that the Earth was spherical, some sort of a sphere, okay? Whichever way you go, it's not just a circular sphere, it's a spherical. There was another argument actually based on the observation of the lunar eclipses. When the moon is eclipsed by the Earth, and that is his argument actually from that time, from antiquity, about 200-300 years before modern era, so BC. So the thing with it is, as the Earth covers the moon, there is a clear arc that forms from the Earth, the shadow of the Earth as it's cast on the moon. No matter which time, no matter which position, no matter where you are during the eclipse, it's always curved. So it's not just a flat disk, somehow flat like a CD-ROM. No, it's actually a whole sphere here, because everywhere you go, you will see the same shape. So if it's a flat disk, and sometimes it casts a shadow, that shadow starts to straighten up to become a line, and then it's going to go back into the, so it's not flat, it has to be a spherical shape. So there was a lot of argument for why the Earth was spherical. There was no problem with it, okay? That's not the issue. The issue are the heavenly bodies. There are two kinds of stars. There are stars, first of all, there are stars that don't move, they are fixed in space, versus other stars. So they form what is known as asterisms, specific shapes. For example, if you draw a shape like this one, you're going to come up with a shape that you're going to say, okay, as long as I see this shape, this is called an asterism, then I have specific shape. They call them constellation, the group of stars that form this shape. I mean, next to them too, they belong to the same constellation. And you have constellations like Orion, Taurus, Leo, Cancer, Aquarius, and Gemini. So those are some of the constellations that you have in the sky, and they were fixed. Okay. And then there are other stars that seem to change from location to location. Like, for example, Mars is a star that is kind of reddish in color that moves from point to point to point. Jupiter does the same thing, moves from point. They don't stay in the same asterism. So if you see them today in Cancer, for example, you might find them tomorrow in Leo. Not specifically, it takes a long time to change because they move so slow, but they do change. Okay, they don't stay in the same constellation. Okay. Venus is another one. The sun, actually, if you want to think about it, also changes constellation depending on the season. Same thing for the moon, but the moon and the sun have different classifications. The point is, Jupiter was known at that time. Saturn was known at that time. Mars was known at that time. Venus was known at that time, and Mercury was known at. So there are 5 moving stars. They call them planets, and the word planets really means a wandering star that moves from point to point to point to point. The trouble with these stars, or these planets, and the moon and the sun, is that they move around the Earth, and everybody else moves around the Earth. So the Earth must be the center of everything, at least visually. If you go outside tonight and you look at the sky, that's exactly what you're going to see. And that's exactly what you're going to conclude. So the Earth is the center of the whole solar system, where all of these things are moving, including the sun revolves around the Earth. Actually, there were some ancients before modern day era, before even Ptolemy, before a long time ago. His name was Aristarchus, yeah. He argued that he was able to measure more or less the size of the sun, and he found it to be bigger than the Earth by about a factor of 20 times, no, about a factor of 7 times, something like that. The point being in here is that he did not make sense to him that the sun would revolve around the Earth, because a bigger object must be anchored more than a smaller object. So his estimates were that the sun is bigger than the Earth. Then he said, okay, maybe it's the other way around. Maybe it's actually the Earth that goes around the sun. Obviously, There was a problem with his explanation, and people immediately rejected it based on scientific observations at that time and the best abilities that they have, and that is a so-called parallax. And the parallax, if you look at, for example, close one eye and look at the tree or whatever, you can, I'm actually in the opposite right now, I can see a tree outside. And then if I close the other eye, the tree seems to shift. This is the parallax. So they said that if the Earth is going around the sun, we should see parallax for the other stars, namely that the stars should shift 6 months from today as the Earth goes around the sun. Since we don't see them, then the Earth cannot be going around the sun. I mean, there is a parallax now. We can measure them with more precise equipment, but at that time, with the naked eye, the stars do not seem to be shifting because they're far away, they're extremely far away. So that's why they don't shift. Okay. So that's the argument that was put against him. Anyway, he basically dismissed it. The ancients also were able to measure the radius of the Earth. Not only they knew that the Earth was spherical, but they were able to measure how spherical it is. What's the radius of the Earth? It's about 6,370 kilometers. That's what the number came in. At that time, they were not using meters or kilometers. They were using stadii, meaning how many stadiums, basically, because the stadium is about 100 meters. I mean, the field of where the action is. At that time, they were using it for other things, not for soccer, or football, or gladiators and things like that. So how many stadia they have? Came up with a very good number, very close from modern day number for the radius of the Earth. And based on the work from previous, they were able to find the distance to the moon, and that number was not too far, actually. The problem was the distance to the sun, which was completely off, and the size of the sun, which was completely off. But the distance Earth-Moon was known. Now we know it's 384,000 kilometers. The distance from the radius of the Earth was known, 6,370 kilometers, and those numbers are important. So 384,400 kilometers is how far the moon is from the Earth. The size of the Earth in terms of radius was known, but with modern numbers, now we're going to take 6,370 kilometers. Roughly 6,400 kilometers, and roughly this is 380,000 kilometers. Obviously, roughly is not good enough if we're going to be measuring precise measurements. Okay, so we're in good shape now. We have a lot of things so far that is known at that point. Mr. Ptolemy later on, toward the about 2,000 years ago, he came up with the classifications of the galaxy. I mean, the galaxy classifications of galaxies were not known until 1923. The constellations, he came up with 48 named constellations at that time, and he also came up with the path of the planets around the sun, the Earth at that time. The Earth was the center of everything, and he came up with an estimate for the calendar, and people were using his calculations to try to predict holidays. When is Easter next time is going to be? When is Christmas is going to be? When is all kinds of religious events? But over time, because there was no precisions in the calculations, things started to shift. Easter started happening later in the fall, for example, and Christmas was happening sometime in the summer. So everything was off big time. So the church hired Mr. Copernicus to fix the calendar. One of the problems that were known at that point was the retrograde motion of Mars. Namely, the star Mars is going around everybody else, like everybody else around the Earth. At some points, it's moving backward. Not only it's not changing constellations like the planets do, but it's actually moving in the opposite direction. So how in the world we're going to explain that? So the idea was that maybe Mars was actually going in a circle. This is what Ptolemy thought, because circles are the regular path. And Mars is actually going in a little circle around the big circle as it's going around the Earth. And that somehow fixed the issue a little bit and gave numbers for Ptolemy that gave him at least accurate accurate predictions up to a few years down the road, but not centuries down the road. Did not work. So the church again hired Mr. Copernicus to fix the calendar. Mr. Copernicus, the first thing he thought is that we had it all wrong. The Earth is not the center of the solar system. The sun is. All of these objects you're talking about, they're revolving around the sun. So the sun is somehow in the center. We have Mercury. Mercury has to be closer to the sun, he argued, because of there is an angle with which it's going to rise and fall as the sun sets. Mercury follows it. Before the sun rises, Mercury leads it, and then the sun follows, and the angle is very small. Based also on that same analysis, he argued that Venus also is the next one, because actually the angle is further away. As the sun sets, Mercury follows, and then Venus later on, okay? This is the maximum. Sometimes it's actually opposite, okay? Sometimes the stars follow, set before the sun. So not every day. So if you go tonight, for example, and you look for the sunset and you don't find Venus, and it's the brightest star there is after the moon. So there is nothing brighter than Venus. And if you don't see it because it fell before the sun, then hey, it's not always so, depending, because it's spinning around the sun as it is going. So sometimes it's ahead of the sun, sometimes it's behind the sun. So that's really what I'm trying to say here. So Venus must be the sun, the next, and then he argued that the Earth is the next, Mars, Jupiter, and Saturn. This is not to scale, okay? So that you guys know. This distance, for example, from the Earth to Mercury is a lot less than from Mercury to Saturn, okay? So that you know. Saturn is about 20 times, about 10 times further from the sun than the Earth is. So the Earth is here. This distance is about 10 times this distance. So this is not to scale. The point being, in here, he came up with a model now, and he was able to explain a lot of things. The only issue that he ran into is that he still retained that circular paths, and that has actually, for philosophical and also religious reasons, why they thought that the circle is perfect and the heavens are perfect. So he argued that that's basically what it was. Mr. Kepler took the work of another person by the name of Tycho Brahe and basically analyzed it and came up with 3 laws. The first thing is that the paths are not circular, they're actually elliptical. So they're part of an ellipse. An ellipse is like a circle, except it doesn't have a single center. It has 2 points of interest. They're called the focal points. So you have one focal point and another focal point. And let me draw a perfect ellipse in here. And there is, what? Come on. Okay, here is an ellipse, okay? We tried to draw it, but it didn't draw it in the right place. Anyway, it has 2 focal points, 1 and 2. Forget about the first 2. Can I erase stuff in here? Yeah, probably. So this is not part of it, okay? This one is this one. Anyway, so this is the ellipse. It has 2 focal points. The sun, he said that it must be sitting in one of them. Which one is which doesn't matter, okay? And the planets go on the ellipse. So the ellipse has 2 characteristics, several characteristics actually. It has this distance, which is called the major axis, and it has this distance, which is called the minor axis, and it has this distance, which is the focal length, focal distance between the 2 focal points. So all of this is labeled A, by the way. Half of this major axis is called the semi-major axis, labeled A, and also half of the minor axis is labeled B, and half of the distance between the 2 focal points is labeled C, okay? There is another quantity also in here, which is the eccentricity of the ellipse, and the eccentricity of the ellipse is how flat it is, okay? So basically that this is the path of all of the planets. Granted, in reality, most of the planets have a very low eccentricity, meaning that they look more of a circular path than the actual ellipse. For the case of the Earth, its eccentricity is very, very low. It's almost 0, which means that the 2 focal points are very close from one another. C is 0 practically. It's very small, and that means that the Earth revolves around the center of the sun for all practical purposes, okay? The sun is hardly budging from the effects of the Earth. take other planets, basically they tend to have a little bit of eccentricity, especially Mars. But that's not really not that high. The Earth eccentricity right now is very small. So that is the first law. The second law basically says that as the planet moves around the sun, at some point it's very close from the sun. This happens for us on December 21st. The Earth is very close from the sun at a distance of 147 million kilometers. Around June 21st, the Earth is very far from the sun, relatively speaking, and that is 153 million kilometers. If you take the two numbers and you divide them by 2, you will find that it's about 150 million kilometers on average, the Earth is, okay? So that's basically from its closest point to the furthest point. So this is basically the now here is the second law. It says that as the planet is going around the sun, it's let me try to get a different color here at the same time. Let me get the red in here. Okay, so as it travels from this point to this point, it's going to sweep this area. Okay, so this area. Let's say, for example, this is in 1 month time. And if it travels, let's say, for example, on a far away distance, the same amount of month, obviously it's going to travel this arc only, not this big arc, smaller arc. But if you measure this area, it's the same area. The same amount of time, by the way, it's a month. So in other words, it's moving slower and it gets further away from the sun on its far away points than when it's closest by. So it's going to come out and then like this. So obviously for the case of the Earth, it's not going to make a lot of difference, but it does on average because of the fact that the distances are not too far. So again, the second law is that the planets actually sweep equal areas in equal amounts of times. Equal areas at equal amounts of time, okay? So that is the second law. The third law actually is the one that is actually a little bit more interesting. And that is, if you take the time it takes for a planet to go once around the sun, so let me choose a different color for right now. And let's get the blue here, this thick blue. The time it starts, let's say, for example, it starts from here. This is December 21st, and then it goes around. This is June 21st. This is September 21st, and now we're back to December 20th. That's 1 year. So the period in this case, for the case of the Earth, is exactly 1 year. Okay. For the case of other planets, it may be more or less. For the case of Venus, for example, and Mercury, it's less. For the case of Mars and Jupiter and Saturn, it's more. At that time, by the way, Uranus and Neptune were not known. They were discovered after this time frame that I'm talking about. So this is that. And then remember this A, which is half that distance. He said the third law basically says that, okay, P squared is actually equal to A cubed, provided A is in years. I mean, P is in years. P squared is equal to A cubed. So those are the three laws of Kepler. P is in years. Like for the case of the Earth, it's 1. For the case of Mars, it's slightly more, it's almost 2, okay? 22 months on something, so for 1 year on Earth, for 12 months on Earth. And A is in astronomical units. What I mean by astronomical units is how far the Earth is from the sun. In other words, one astronomical unit is 150 million kilometers. Obviously, for Venus and Mercury, A is less than that of 1 astronomical unit. For the case of, for example, I mentioned already, Saturn, it's about 9.5. And for the case of Jupiter, it's about 5.2. And for the case of Mars, it's a little over 1.5 astronomical units, basically time and a half further away from the sun than the Earth is. So that's what that is. So that's the third law of Kepler. So these are the three laws of Kepler. We are in the time of the early 1600s when he came up with them. Then Mr. Galileo came up with his observations and stuff like that, and he died in 1642. Around the time when he died, Mr. Newton was born. And I mean, within a few months, actually, he was born. And then Mr. Newton went to school, and as he was in college in his early 20s, he came up with 3 laws that we discovered them. The first law is the law, basically, if an object is under no net forces, the object will retain its motion and continue in the straight line forever and ever and ever. And if the object is under net force, it's going to accelerate so that its acceleration is the ratio of its force over its inertia. And the third law, if 2 objects interact, they do so in such a way that if one object exerts force, the other one exerts a force that is equal in magnitude in opposite direction. So those are 3 laws. He came up with them while he was a student. So the plague hit London around 1660, and everybody was sent home, including himself. And I don't really forgot the name exactly who did that, but somebody brought him these 3 laws of Kepler, and he told them, okay, you came up with 3 laws of mechanics that you think can explain everything. Can you explain these 3 laws? That's really how the challenge was. So there was no apple that fell on his head so that he could come up with it. In doing so, he tried to explain it. He made an argument. Forget about these planets, business, Mars and Jupiter and all of these things I was talking about, and Saturn and later on Uranus and Neptune and things like that. I'm going to he said, focus on the moon as it goes around the Earth. And compare that to an apple and how it falls on the ground. That's basically the whole argument that he did. As he compared the two, he came up with this law of gravity, the one I mentioned earlier. And this law of gravity, excuse me, there are people outside in here. Let me pause this thing in here quickly. Anyway, the point being in here, as that time basically came in, he tried to make the case for, or at least try to explain this by comparing, like I said, forget about the planets. He wanted just to focus on these two. An apple falling to the ground versus the moon continuously going around the Earth, but he argued actually it's maybe the same thing, maybe the same force. By the way, the force of gravity that later on basically became the force of gravity that he postulated was at that time suspected in a sense big time that he's part of the explanation for that. At least it was hinted in the work of Copernicus and later on for the work of Kepler, but there is no formal form for it. It was not really formally written, at least in this form. Okay, so. And why is this thing not moving in here? We try to click out of it. Now it's moving. Anyway, so what Mr. Newton did is the following, and it's really a very good argument that he used, okay? Here is the argument. The Earth and the apple are interacting by force of gravity, which we're going to need in the lab later on, which is the weight of the apple, which is mg. Okay, that is how the apple falls. If you take an apple and drop it, it's going to fall to the ground due to this force, mg. Where m is the mass of the apple, by the way, and g is 9.8 meter per second squared. The mass of the apple in kilogram. So this was known by the work of Mr. Galileo already. He argued also that what's going on in the case of the moon is that it's going around the Earth with a certain velocity, which I can compute, by the way, if I know this distance, which is the radius, basically, which is 384,000 kilometers, by the way, the number that we talked about. And if I know that the moon goes around the Earth in 27.3 days, and that was a known fact, then I can find the speed with which it's moving. Basically, it's just the circumference divided by the time, because it's going to go in a circle. The circumference, I'm going to multiply 2 pi times 384,000. This was one of the problems, by the way, of the homework. 384,000 or 384 million meters, because remember, I have to use meters per second at the end. So it's 384 million meters times 2 pi. That gives me the path that the moon takes to go once around the sun. Once around the Earth, which is 1 lunar month. Sidereal, but there is a distinction between the two because the Earth is moving around. As it moves around, the moon has to take extra 2 days actually to adjust itself so that it's looking to the same from new moon to new moon, really. That's how the lunar months are calculated. So because of the rotation of the Earth, it's actually more than 27.3 days. So it's divided by 27.3. But that's in days. I want it in seconds because remember, these laws of Newton require meters per second. So I have to multiply 24 hours in 1 day because this is the number of days, number of hours in a day. And every day has 60 minutes, and every minute has 60 seconds. So 60 times 60 is 3,600. And that is the speed with which the moon goes around the Earth. Then I know the acceleration of the moon. So the mass of the moon, which I'm going to label it m with lowercase m, times the acceleration. And the acceleration, I know exactly what that is. It's a v squared over r. So if I can compute this v from here and divide it by r, and r is 384,000 kilometers, or 384 million meters. So now I'm in business, basically. I know exactly where the acceleration of the moon is. The interesting part, and that was part of the homework that we actually worked out last time, is that the ratio of the acceleration of the moon over that of the apple, you take 9.8, you divide it by this acceleration, you're going to find the ratio is about 3,600. So that's the ratio. It has no number. It has no dimensions. It's just a number ratio. It's just a number. And if you take this distance, 384,000 kilometers, basically the distance from the Earth to the moon, and you divide it by the radius of the Earth, which is about 6,400 kilometers or 6,370 kilometers, you're going to find the ratio is about 60. 60. So this is the ratio of the radii. Okay, if you wish, or the distances, okay, radius to distance. It's actually the other way around, distance of radius, okay? And this is the ratio of the acceleration, that of the apple versus the moon. And if you take the square root of this number, you will find it's exactly 60. Square root of 3,600 is 60. So the distance matters in terms of its square, really. So as the distance increases, you need its square because this is the ratio of the distances. That's why, and it decreases because it's less for the moon than that of the Earth by this factor of the square. That's why you have an r squared in here. Then here is in the following. If you are on the Earth, like the case of Newton or myself, okay, looking at the apple as it's falling to the ground. Where is the Earth and the apple that you started with? It's in here. Okay. So if you are on the Earth trying to do the experiment with the apple, and you drop an apple, you say its weight, it's being attracted by a force of mg, where this g is basically that acceleration due to the Earth. Okay. So that's for your vantage points. Remember the action and reaction principle, the third law of Newton. If you are a worm living on planet Apple, this is your planet, of course, you're sitting on the planet, and you see the Earth falling towards you with the same effect. Obviously, you're going to conclude that that force is going to be equal to the mass of the Earth times the same g. Because if you're doing another experiment in there, instead of dropping the Earth on you, you could drop any smaller object and you should be able to find its mass times the acceleration. So he argued that since the mass of the apple comes into this expression from the vantage points of Earth, and the mass of the Earth comes into this expression from the vantage point of the apple, then in this situation, the product of the two masses must be in m1 times m2, where m1 could refer to the mass of the apple and m2 would refer to the mass of the Earth. So that's the whole argument. There was a problem, though, with this law. Two problems. First of all, we need to work out the numbers in such a way that 9.8 still works for the case of the apple and the Earth. That's one thing. And the second thing in here is that the units don't match because I have a kilogram in here times a kilogram, that's kilogram squared, divided by distance squared, that's meter squared. And that is not how we said MA. MA, remember, is a kilogram times a meter per second squared. I don't have enough units in here to match this two. So I have too many kilograms in here. I need just one. And I have the meter, but it's in the opposite direction, so the denominator. So I'd like to multiply this number by meter cubed to cancel this meter squared and make it match. And then I have to divide by one of these kilograms to make it match. Not only that, I have a problem with the time. I don't have enough time in here. I have 1/2 squared and I have nothing in here. So in order to fix that, I have to have this second squared. So in this case, this will fix the problem for me if and only if this G will have this units. So if it's G has the units are meter cubed over a kilogram per second squared, then I multiply it by a kilogram and a kilogram. One of those 2 kilograms will cancel this kilogram and I will be left with a kilogram in the numerator. And when I divide by meter squared in here, because that's what the square of the distance is, and I have a meter cubed in here, one of this 2 meter squared in here from the meter cube will cancel a meter squared, and I will be left with one of them in the numerator. And this second squared will stay intact as it is. So the dimensions are fixed, but the numbers also have to be fixed too. And that's where the value of this G is needed, actually, both value and units too. So for the case of the apple on the earth, apple, or any object for that matter on the earth, okay, the force is actually MA or mg, okay, we call it G. And this must be equal to big G, the number that we introduced, times the mass of the apple times the mass of the earth divided by, in this case, it doesn't matter. Let me explain why that is. What distance is, because here is the problem. The earth is huge, okay? This distance, 6,370 kilometers. When we drop, or 6,370,000 meters, because we're doing in meters. Hey, this number, so this is the distance from the center of the earth in here. And when we drop an apple, we drop it probably from a meter distance height. 2 meters if you really want to smash the apple. 10 meters if you want to obliterate it. And even 10 meters is nothing in front of 6,370,000 meters. So it's really nothing. So in this case, it's the radius of the earth, which is 6,370 meters, but I mean 70 kilometers, but I cannot use kilometers when I'm dealing with units like this one here. Squared. Don't forget to square that distance. So these two must match. The number G to work out these things is 6.67. And it has to have those units, as I mentioned, meter cubed per kilogram per second squared to cancel 2 of the meter squared in the denominator and to cancel also the 1 of the kilograms in the numerator, and to also need that second squared in the denominator so that everything works fine. So we need that. So that's the units times 10 to the power -11. So it's a very, very small number times the mass of the apple times the mass of the earth. The mass of the earth, if you Google it, it's about 6. It's slightly less than 6. So I'm going to round it to 6 times 10 to the power 24 and divide the whole thing. Divide the whole thing by this number squared, okay? 6,370,000 meters squared, okay? Now, this must be equal to the weight of the apple, mg. Cancel the m of the m. So that's why it doesn't matter really if we're talking about an apple or talking about the mass that we dropped the other day in the free fall, or talk about any mass that falls on the earth, as long as it's small enough. It doesn't matter really, but if it's not that small, because it's going to cancel anyway. So the value of G really should be, remember, G is about 9.8. Okay, that's what Mr. Galileo found. G must be then 6.67 times 10 to the -11. I'm approximating the number, so I'll be slightly off, but that's not really the point in here. the point in here is the value of G, and I will explain the big G, not small g. The mass of the Earth, which is 6, I'm approximating this number, 10 to the power 24, divided by, this number also is approximate. It's not exactly 6,370 kilometers, slightly off, okay? So we really technically should put, I think, like 74 or 72, and I don't remember the exact number. So let's switch calculators. Let's go to a calculator and make sure that we get this thing correct, okay? So let's go back into, do we have a calculator? I don't. Let me first of all start the calculator in here. Calculator. And it's in scientific mode, so that's good. So let me share the calculator. Okay. So the first thing I said in here, 6.67 times 10 to the negative 11. I really don't know how to do 10 to the negative 11, although having to do open parentheses in here, minus 11, close parentheses. That's the only way I know how to do a negative sign in this calculator. 10 to the negative 11. Here is 10 to the negative 11, and this is the number. 0.0000. I don't know how many zeros, 11 zeros. Anyway, the point being here is that is 10 zeros plus 6, plus 1 0, one digit for the other zero. Anyway, so this is 6.67. That is G, big G, times the mass of the Earth. The mass of the Earth, I'm approximating it to be 6 times 10 to the power 24. So I'm going to write 24 and then to the power. This is in kilograms, by the way. This is how much the mass of the Earth is. 6 times 10 to the power 24. Okay. So this is the numerator. It's a big number. Yes, it's expected to be a big number. Divided by the square of that radius of how far the apple is from the center of the Earth. So divided by, I'm going to do an open parenthesis again. What I'm going to write in here is, let me write the whole number, okay? Yeah, but we're going to square it. 6,000 or 6,370,000. So I need 3 more zeros. 1, 2, 3. And the whole thing is squared. This number is squared underneath. This is what the square is. So now if I do the ratio of these two numbers, it's looking good. And here's square of this number. So it's 9.86, okay? It's not exactly 9.80. Even the value that I've been posting, 9.80, is slightly off. It's not actually 9. Slightly more than 9.80, but it's slightly less. I mean, it's less than 9.86 because we overestimated the value of the mass of the Earth from its actual value, 5.9 something. And we underestimated the value of the radius. Actually, remember, if we put more than what it is, so it's slightly more, so it's going to bring this number to the correct value, which is 9.8. So this is how big G is. So let me go start sharing in here, and let me share back the screen where I was scribbling with my mouse. According to the calculator in here, this is 9.86, okay? I'm gonna leave the 9.8 in here because the 6 has no bearing in here because of these approximations. Again, the units, because we fixed the units of G so that everything matches, is meter per second squared. Now here is the thing. This is the value of G on Earth, little g, gravity. But the problem is actually backward. The problem is Mr. Newton actually argued for the value of big G being 6.67 times 10 to the negative 11, based on the fact that he knows the value of little g. So in other words, you take this value and equate it to, you take G times the mass of the Earth and divide that by the radius of the Earth squared, and you force that to be equal to 9.8. Okay, since you know the value of the mass of the Earth, or you actually have an estimate for how much it is, since you know the value of the radius of the Earth, and that was a known fact at that time, then the only thing that is missing from this equation is the value of big G, and big G will emerge naturally from this requirement, as he did, as 6.67 times 10 to the negative 11. Again, the units have to match, so it needs a meter cubed in here, and it needs to get the acceleration correctly. So we need a meter cubed in there, and we needed a kilogram in here, and we needed second squared in here. Okay, An alternative unit that you might find in the literature is actually Newton divided by a kilogram squared times a meter squared. Newton meter squared over a kilogram squared. That's also similar. So same thing. Now, this whole discussion that we had up to this point, the Earth and the apple, the Earth and the moon. And he said, you know what? I'm going to take that same stuff and now apply it to the sun as the planets go around it. So the law changes now. Instead of the mass of the Earth and all of that, G, he said it's the same thing. The mass of the planet now, so this M is the mass of the planet, and this M is that of the sun, okay? And divided by how far the planet is from the sun, squared. That's it. Basically, that's the law that he did. He took these equations and he did a little bit more work, and he was able to reproduce all this stuff. Okay, everything up to this point, all of the 3 laws of Newton. Okay, all of them well explained perfectly. The only trouble was planet Mercury that gave him a headache because it has an error in it. So Mercury was a puzzle for several centuries until Mr. Einstein came up with a better explanation than this law of gravity. And now Mercury also is explained, including black holes or some other stuff that this law cannot explain, honestly. Okay. So there are limitations, but those limitations are way outside of our daily experience. On a daily experience, this is a perfect law, where G is 6.67 times 10 to the negative 11. So this is basically the context with which the law of gravity was discovered. And this is basically the force of gravity. Obviously, for the case of a planet, I have to equate that to M equals to MA, where that A actually has 2 components in it, because the planets, as they go around the sun, they are not really going with constant speed to say it's just B squared over R. They're going actually on a different path, that elliptical path. So sometimes we always have a tangential acceleration, and we have actually a centripetal acceleration, which is always V squared over R. And then the only trouble with that also, as the planets go around the Earth, the problem becomes far more complicated. Around the sun, I'm sorry, the problem becomes more complicated. Because if I take Mercury, Mercury is being influenced by the sun, of course, and it's the biggest player, but it's also being influenced by Venus, and it's influenced by Earth, and it's influenced by probably Mars, especially Jupiter, and Saturn, and Uranus, and Neptune, and a bunch of other tiny stuff. So the problem is very complicated for a single planet. As a matter of fact, the far reaches of all of the stars will have an influence. So this law does not drop to zero, it's always there, okay? So the problem becomes far more complicated, and the situation is understood. In that sense, you have to really work with it. Okay. Why the R squared? This is another reason also why we have it. The inverse square law. Inverse square law. Okay. If you take a candle, for example, or a light source, I mean, we don't have any more candles nowadays. We have a light bulb, okay? Light bulb is fine, okay? And you light it, and you're immediately next to the light bulb. Well, you can read the book, you can see things, you can do whatever you want to. Move about 10 meters away from it, and the light starts to dim, provided there are no other sources away from it, okay? And it dims by a factor of 100 compared to 1 meter away from it. Okay, so if this is 1 meter, and this is 10 meters, the light drops by a factor of 100, meaning things you could do easily while you were next to the light bulb are far more difficult now, like reading a book, for example. 10 meters is a lot. It's about 33 feet, okay? Now, if that's not enough for you and you have a strong enough light bulb, you're fine. Move another 100 meters away from it. Well, I'm sure no matter what light bulb you're using, it's going to be hard unless you have one of those floodlights, okay? And those are still not going to really. You have to have many of them to have a full stadium at night lit, okay? But it's still, if you are very close from it, it's going to be 10,000 times more brighter than if you are away from it, but it's still far. And if that's not enough for you, well, move a kilometer away, move 1,000 meters. Then even if it's a floodlight, it's not going to have that much of an effect. because it's going to drop by a factor of 1,000,000, the lighting. So let's explain why that is for the case of light, and it's the same effect probably for the gravity in this case. So you have a light source in here. Next to it, the light will spread through a sphere, not a circle. I mean, I can draw a sphere on a flat screen, but that's because it's a sphere. And as you move away, the sphere expands in radius. So the sphere, it's the same sphere where you have the light concentrated on a very small radius, but as you move away, it's the same light that started initially from the light source, but now it's spreading over a bigger and bigger surface. And because the surface of the area is 4 pi r squared, so the same amount of light that was concentrated in a small r, now it's on a bigger r, bigger surface. That's exactly what's going on in this case. The same thing, by the way, is for the sound too. If you are near the source of the sound, you can hear it very well because the sound is actually concentrated. As you move away from the sound, again, it drops like 1 over distance squared because spreading over that much of the sphere. The same thing, by the way, for your signal on the phone too. Oops, desk concern. So as the phone also actually and basically, as you move away, again, it's going to drop with that signal. Actually, the bars will drop away as you move away from the tower. That's basically the same thing, and it drops with the same factor. So this is the inverse square law, and actually, it's a consequence of the fact that we live in this universe, which is three-dimensional universe. So areas drop like 1 over square laws. For living in a different universe, probably a 4-dimensional universe, will have a cubic law, so they would drop much faster. So that's basically one of the phenomena that is, and it has to do with how light spreads. So again, that shows itself in here. When we explore electricity, we will saw similar light, the similar law also for the how electricity changes with distance, and it's exactly the same behavior, 1 over the distance squared. As a matter of fact, Mr. Kepler brought this point in his analysis about how the planets go around the sun, and he thought that there is some sort of a magnetic force that forces them to go around the sun in those circles, and the magnetic force also drops with 1 over distance. And the same analysis, because of the planets as far away, they have the less magnetism than the planets nearby, and at that time magnetism was not well understood, but then we have a better explanation for it through Mr. Newton's laws. Okay. I know this went a little bit longer than the planned sessions, but here is the point. This law explains a lot the behavior of the planets, and it explains a lot the behavior around the Earth also. One of the applications is the so-called geocentric satellites. So what it is if you want to have a satellite facing Earth all of the time, meaning I use that satellite to look at it right now. If the Earth spins, and it spins when it does 1 full rotation in 24 hours, I would want the satellite to stay immediately above my head. It doesn't change location. So those are so-called geocentric satellites. They must align themselves, meaning they have to spin exactly as the Earth is spinning around its axis. They do 1 full rotation around the Earth in 24 hours as the Earth is moving around. So those are important, and they obey the same law that we were talking about in here, the accelerations and all of these things. They're all expressed in terms of all of these relationships. So again, they have interesting applications because one of the applications is, first of all, we wouldn't want them to be, they have to be on the equator, number 1. And then the other thing also at least launched so that they orbit the Earth around the extended version of the equator. And then they have to be in a specific distance where the period P must be equal to 24 hours. Because remember, this is Kepler's law. Kepler's law is still 100% explained by this one, meaning P squared is equal to A cubed, how far they are from the Earth. Granted, P in this case is exactly 24 hours. So this number changes for the Earth big time. So there is a number in here, a constant of proportionality that needed to be found. Which brings me to an interesting point. Mr. Newton explained the work of Kepler. That's good. But if that's all he did, that is not good, actually. He needed to go a step beyond. For a theory to become acceptable in science, and especially in physics or astronomy, you have to really go, you cannot just explain what has been observed, what has been measured. And that is one of the things that Mr. Newton did, actually. He went a step further. He found that this ratio, what does that have to do with anything? okay, the ratio of these two numbers. And it has to do with the mass that's being orbited. For the case of the sun, the mass of the sun. For the case of the earth, the mass of the earth. For the case of the moon. And for the case of Jupiter, and that is actually what Mr. Galileo has observed. There are those 4 moons of Jupiter that go around it, namely Io, Callisto, Ganymede, and Europa. As they go around the Jupiter, they were able to find the mass of Jupiter using that because of that ratio. So we want to step beyond. Then a comet appeared at that time, well after the work of Mr. Newton. And Mr. Halley actually predicted when it's going to come back, because based on how much arcing it's going to do, he was able to find and use the number from the Earth, and he found P in that case. And based on that, I mean, he found A at that time, and he was able to estimate A, not exactly found it. Based on that, he predicted that in 76 years and so many days, it's going to reappear again. Well, after he passed away, the comet reappeared again and now bears his name, Halley's Comet. Okay, so that you can understand the idea behind all of these things in here. So now it bears his name, and it's really, so you went a step beyond. So you could do more than that. Now it's actually the same law is actually used for the binary stars and things like that. So it's really a very, very, very important relationship and important concepts. Since the time is actually running out at this point, I'm going to stop right now. We're going to post the recording, and I will see you guys later in the lab. And if you guys have any questions, please do not hesitate to send them. Thank you.